Section 2. 6.
Pure science may seem useless in the usual sense, but over a long period of time, it surely leads to economic and technological benefits. If we stop paying for pure science today, there will be no applied science tomorrow. Charles Darwin's work on evolution and Gregor Mendel's on the heredity of plants laid the foundations for the science of genetics, which eventually led to the discovery of DNA, which led to genetic engineering, which is now exploding with unimaginable applications. Michael Faraday's discovery of how a magnet can produce electricity made possible the first hydroelectric power plant 50 years later. Yet Darwin, Mendel, and Faraday were not supported with any such profits in mind, nor could they have been. A nation cannot bet on pure scientists like betting on horses. It can, however, build stables. Discoveries in pure science are not just about nature. They are about people as well. After Copernicus, we have taken a more humble view of our place in the cosmos. After Darwin, we have recognized new relatives hanging from the family tree.
Seven.
If a scientist believes a certain hypothesis is true, but finds contradicting evidence, then in the scientific spirit, the hypothesis must be changed or abandoned. In that same scientific spirit, the idea must be changed or abandoned in spite of the reputation of the person advocating it. As an example, the greatly respected Greek philosopher Aristotle claimed that falling objects fall at a speed proportional to their weight. This false idea was held to be true for more than 2,000 years because of Aristotle's compelling authority. In the scientific spirit, however, a single verifiable experiment to the contrary outweighs any authority, regardless of reputation or the number of followers or advocates. Scientists must strive to distinguish between what they see and what they wish to see, for they, like most people, have a vast capacity for fooling themselves. People have always tended to adopt general rules, beliefs, creeds, ideas, and hypotheses without thoroughly questioning their validity, and to retain them long after they have been shown to be meaningless, false, or at least questionable. The most widespread assumptions are often the least questioned.
Eight.
A paradigm is a general theory, like the Darwinian theory of evolution, which has achieved general acceptance in the scientific community. Paradigms help scientific communities to standardize their discipline in that they help the scientists to create avenues of inquiry, formulate questions, select methods with which to examine questions, define areas of relevance, and establish or create meaning. A paradigm is essential to scientific inquiry. No natural history can be interpreted in the absence of at least some implicit body of theoretical and methodological beliefs that permit selection, evaluation, and criticism. Then how are paradigms created? And how do scientific revolutions take place? Inquiry begins with a random collection of mere facts, although often a set of principles is already included in the collection. During these early stages of inquiry, different researchers confronting the same phenomena describe and interpret them in different ways. In time, these descriptions and interpretations entirely disappear, and a pre-paradigmatic school appears. Such a school often emphasizes a special part of the collection of facts. Often, these schools compete for supremacy. From the competition of these pre-paradigmatic schools, one paradigm emerges. To be accepted as a paradigm, a theory must seem better than its competitors, but it need not, and in fact never does, explain all the facts with which it can be confronted, thus making continued research necessary. As a paradigm grows in strength and in the number of advocates, the other pre-paradigmatic schools for the previous paradigm fade, bringing about a great change in science.
9,
Ptolemy's view of the solar system was accepted for 1400 years until finally challenged by Copernicus, a mathematician and astronomer with a Polish father and a German mother, in 1530. Copernicus's view of the solar system had the sun at the center, with the Earth revolving around it, along with all the other planets. Shown here is the picture from his original publication. As can be seen, the only thing that doesn't go around the sun is the moon, which continues to go around the Earth. One objection that people had to the picture was that if the Earth was indeed just another planet, how come it was the only one with a moon? Other objections included, why does it feel like the Earth is standing still, and why don't objects thrown into the air land far to the west? Also, if the universe had been created for mankind, then why wasn't mankind at the center? Despite these problems, Pope Clement VII approved of Copernicus's work in 1530 and asked for a copy of the full work when it was available. This was not until 1543, the year that Copernicus died. The real breakthrough that ultimately led to the general acceptance of Copernicus's theory was due to Galileo, but was actually a technological rather than a conceptual breakthrough. It was Galileo's improvement and use of the telescope that persuaded people that the moon was a lot like the Earth, and in some ways, so too were the planets.
Ten. In 1978, NASA scientist Donald J. Kessler envisioned the possibility of a cascading chain reaction of space debris collisions taking place in low Earth orbit. This chilling potential scenario has since been dubbed the Kessler syndrome. The underlying mechanism of the concept is that an impact between two man-made objects in space will generate further debris, leading to an exponential number of subsequent collisions, culminating in a situation in which a deadly swarm of shrapnel and space junk circles the planet, devastating everything in its path, including functioning satellites and manned spacecraft. Kessler made the pessimistic prediction that the density of space junk in orbit around the Earth would, by the year 2000, reach a level at which random collisions were inevitable. Although man-made objects in space were already being cataloged at that time in the interest of anticipating and avoiding collisions, the additional objects generated by such collisions were not being tracked and were often small enough to escape satellite detection. Kessler proposed a reduction in the number of objects abandoned in orbit after they had ceased to function, hypothesizing that this would be the most prudent way of preventing future accidents. However, it wasn't until a 2009 collision between two communication satellites, one Russian, the other American, unleashed thousands of small pieces of debris into orbit and potentially set into motion Kessler's doomsday scenario that international efforts to authoritatively address the situation were undertaken in earnest.